sklearntreeDecisionTreeRegressor. Description: Decision tree regressor is a supervised learning algorithm used for regression tasks in machine learning. It builds a tree-like structure where each internal node represents a feature. Each branch represents a decision rule based on that feature. And each leaf node represents a prediction for the target variable. The model learns from data by recursively partitioning the feature space based on the best split points that minimize the prediction error. Inputs: X, the training data containing the features used to predict the target variable. It should be a 2D array or a pandas data frame. Y, the target variable values for the training data. It should be a 1D array or a pandas series. Outputs: predictions, the predicted values for the target variable for new unseen data. These are obtained by traversing the decision tree from the root to a leaf node based on feature values of the new data. Decision tree model: a trained decision tree regressor object that can be used to make predictions and analyze the decision-making process. Steps: data preprocessing: the input data is typically preprocessed to handle missing values, outliers, and to scale or normalize features. Tree construction: the decision tree is built recursively. At each node, the algorithm iterates through all features and selects the one that results in the best split, based on a chosen impurity measure like mean squared error (MSE) for regression. Pruning: to prevent overfitting. The decision tree might be pruned after construction by removing branches that do not significantly improve the prediction accuracy. Metrics: mean squared error (MSE) measures the average squared difference between the predicted and actual target values. Lower MSE indicates better model performance. R-squared R2 measures the proportion of the variance in the target variable that is explained by the model. Higher R2 indicates better model performance. Visualization plots. Decision tree visualization: the decision tree structure can be visualized as a graph showing feature splits, branches, and leaf nodes. This helps understand the model's decision-making logic. Fine-tune parameters. Criterion defines the impurity measure used to evaluate the quality of splits, e.g. MSE for mean squared error. Max depth limits the maximum depth of the tree to prevent overfitting. Minsamples split: the minimum number of samples required to split an internal node. Minsamples leaf: the minimum number of samples required to be at a leaf node. Max features: the number of features considered for splitting at each node. Uncertainty methods. Bootstrap aggregating bagging: multiple decision trees are trained on different subsets of training data and their predictions are averaged to reduce variance and improve the models. Robustness. Challenges and fixes. Challenge 1: overfitting: when the decision tree is too complex. It might perfectly fit the training data but generalize poorly to unseen data. Sample use case that resulted in challenge 1: a decision tree with a large depth might capture noise in the training data, leading to overfitting. Fixes to challenge 1: reduce the tree's depth using the max depth parameter. Increase the minsamples split and minsamples leaf parameters to prevent splits on small subsets of data. Apply pruning techniques to remove unnecessary branches. Challenge 2: sensitivity to noise: decision trees can be sensitive to outliers and noisy data points. Sample use case that resulted in challenge 2: a few outliers in the training data might significantly influence the split points, leading to poor generalization. Fixes to challenge 2: preprocess the data to handle outliers, such as removing them or transforming them using robust methods. Consider using ensemble methods like random forests, which train multiple trees on different subsets of data and average their predictions. reducing the impact of outliers.